In this video, we will introduce some advanced CNN parameters. So in the previous video, we have discussed the usage of the CNN operations, and now we will try to introduce some more parameters to customize the computational layers to increase the power for it. The first one we want to discuss is one-by-one convolution. In a typical CNN layers, we will have a kernel whose size is 3 by 3 or 4 by 4. So that for the 3 by 3, we will take a look at the 9 pixels in the input data and use all of those 9 pixels to make a decision about the output channel. But what's about the one-by-one convolutions? For the one-by-one convolutions, we look at the single pixel in the input data only. So it means that we will not try to detect the features across to the two-dimensional space. So, but instead of the detect feature in the two-dimensional space, we detect the feature in days. So, for example, in here, we have the one set of the CNN operations, CNN kernels, one-by-one CNN kernels, and actually we take the three pixels from each of the channels, and then we take a weighted sum of all those pixels to produce the output. And in here we have a two set of one-by-one kernels. So we will take the other set of weighted sum and produce the output in the other output channels. So it means that, for example, if we using the color space conversion as an example, in this case, the input is the color image. So we have three channels here, one for R, one for G, one for B. And then our output channel will be a single channel. So in this case, we only need to have one set of the one-by-one kernel. Then we can use in the formula here to convert the color image to the monochrome image. And the three numbers here are the weighted for each channel. So it means that the three number will be the three CNN kernel here. So we can using the one-by-one convolution to convert a color image into a monochrome image. So this is a good example to explain what the one-by-one convolution is. So in general, the one-by-one convolution is using to change the number of the channels. Okay. And there is other options in the convolution layer. And we list three of them here. One is the dilation, the other one is the group, and then the bias. The bias is the easiest one, because in some situations, we don't really need the bias term in the convolution. So we can, in that case, we can set the bias to be the false. For example, if we have a CNN layer, convolution layer, and we have a batch normalization layer, in this case, the bias term of CNN can be put into the batch normalization layer. So we will set the bias term in the CNN to be false, so that we can reduce a couple of parameters without affect the performance of it. And for the dilation and the group uh, parameters, they will be using to implement some special type of a convolution. Let's try to look at it. So for the most basic CNN layer, we can using this function to define it, the NN dot COMV 2D. And for this function, we can specify the number of input channel, number of output channel, and the kernel size. Those three are required. And actually, we can write the function in positional parameters way so that the program will look like more concise. So we just put the input channel, output channel, and the kernel channel as the first three arguments for the COMV2D function. But in fact, I would suggest to using the next argument. It will be more obvious for the reader to understand your programs. Although you need to type more characters, but today's by using AI assistance text editor, the text editor will fill those arguments for you, so that you don't really need to type so many characters. So the next item we want to discuss is depth-wise the convolution. So if you remember, in a normal convolution operations, we were using all input channels to produce the result of all output channels. But in a depth-wise convolutions, uh, we will use only one input channel to produce the result of the output channel. For example, in the program here, we let the input channel, the number of input channel, to equal to the groups. So it means that the groups means that how many groups we want to divide the input channel. So if they are the same, it means that we are using a single channel to produce the output channel only. So for the example here, for the each of the input channel, we're using the one CNN filter to produce the output channel. So in this case, if we set the group to be non-zero, we must be careful about the output channel because they need the input channel, output channel, and the group must be matched so that we can produce the correct result. Otherwise, the PyTorch will report some errors here. So, of course, you can set the group to be not one and not equal to the input channels. In this case, we will the PyTorch will try to divide the number of input channel by into the group specified group here. For example, if the input channel is 6 and the group is 3, so it means that the 6 input channel will be divided into 3 groups. Each group has 2 channels, and we're using the two the 3 groups to produce three output channels. But in practice, most of the time, the groups will either to be 1 or to be equal to the input channels. We seldom use the other numbers. And the other extreme is the pointwise convolution. So this is just the one-by-one convolution we have discussed. So in this case, we will set the kernel size to be 1. So it means that we will using the one-by-one kernels to do the job. So in this example, we have 3 input channels and we have 2 output channels. So for each of the one-by-one kernel, you will try to produce 1 output channel by using all 3 input channels. And since we have 2 sets of the one-by-one kernels, we will produce 2 output channels. And the other parameter is the dialectic. Dialectic means that we will add some space in the input channel, or when we get the pixels, we will skip some pixels. For example, here we will take the first pixels and skip the second one and take the third one, and skip the fourth one and take the fifth pixels. So that in this way, it's still the 3 by 3, but actually the 1, 2, 3, 4, 5, you will get the pixel from a 5 by 5 image. So it is a technique which can explain the kernel by inserting holes between its elements. So in simpler terms, it is the same as convolution, but it involves pixel skipping, so to cover a large area of the input. Therefore, the dialectic convolution can extend the reception field in the same computation cost. Because we're still doing the 3 by 3 CNN operation, the computation cost is the same, but we can see the larger reception field. For example, if we're using the original 3 by 3, we can get this area only, the 3 by 3 area only. But by using the dialectic, we can increase the reception field to be the 4 by 4. The other thing we want to discuss is polling. Polling will reduce the size of the image maps. So in early stage of the CNN, polling is the only way to reduce the resolution of the image. Of course, we have added a lot of other fields like a dialectic, like a stripe, and which can reduce the size of a feature map as well. But the polling is the most obvious way to reduce the size of the feature map. And we have 2 types of the polling. The first one is the average polling. So the average polling is an intuitive choice of the polling operation because of the image resize. So that in the image resize, we will reduce the size of the image by 2 by using the average polling here. For example, in here, we will using those 4 pixels to produce a pixel here. And we can reduce the 4 pixels to produce the pixel here. So for this one, we just take an average of those 4 pixels. And for this one, we'll take the average of those 4 pixels as well. But today, we seldom using the average polling. Instead, we are using the maximum pooling. The maximum pooling is simpler since that we don't really need to do any mathematical calculation. We only need to we just need to take the biggest number from all pixels. For example, in the maximum pooling, we get the 4 pixel here, and then we just pick the biggest number as the value. For example, in this case, it will be 4. And if we look at those 4 pixels, and it's 1, 2, 4, 5, so the biggest one is 5, so it will become 5. So we can do the same thing to get the maximum pooling of the input to generate the output. And the max pooling is usually used at the middle of the network to reduce the resolution. You will pick out the maximum value of all pixels. So therefore, you will be equal to select one of pixels from all pixels without any mathematical computation. Okay, so we have discussed most operations used in a normal convolution neural network. So let's look at the most simple and the most early CNN networks, the LARNet file. So in the LARNet file, we have 2 convolution layer and the 2 pooling layer. Then the fully connected layer. So you will using the convolution layer to produce the 6 convolution layer, and then using the pooling layer to reduce the feature map by 28 from 28 by 28 to the 14 by 14, and it still has the 6 layer here. And then we're using the other convolution layer to produce the 16 10 by 10 convolution. The output, the feature maps. And then we're using the pooling to reduce the size from 10 by 10 to 5 by 5. So in this case, we have the 16 multiplied 5 multiplied 5 variable in the feature map, and then we just flatten all the pixel here, and then convert it into a 3 vector whose size is 120 and 84 and 10. So we can make a prediction to predict what the digital is. And the LARNet is quite successful at its time, so it can use it to handle the data set called NIST. So I guess most of people has using this data set to do some experiment, and the LARNet use the most of the basic CNN layers we have discussed. So we can try to use in the LARNet to do the digital recognition. So if you are interested, here is the link, so that you can use this notebook to implement a LARNet and to try to train a handwriting digital recognition program.